This is a continuation of lesson 2.1, and it's on algebraic vectors, but we're going to talk about it in 3 dimensions in this video. Okay, so I'm super excited to teach this to you because, well, when do you ever get to draw something in 3 dimensions in like math? Okay, so this is what 3 dimensions looks like. We represent it by r cubed. Okay, so that cubed means you're talking about the x-axis, y-axis, and z-axis. So in a coordinate, normally you would have like 2 numbers, but now that we have 3 dimensions, we're going to have 3 numbers. Okay, and any of those numbers can be all real numbers, and they have to go alphabetically. You're always going to do the x and then the y and then the z. Okay, so on the left-hand side, you can see this gorgeous diagram of a 3-dimensional coordinate system, and it is just beautiful. Okay, so how do you draw? Yes, you're expected to draw this. Okay, so how do you do that? You can use regular graph paper. I'm going to show you how to do that. Or sometimes I find that it's easier to use something called isometric paper. You can Google that, just Google isometric paper, and you can print some of those off, or I guess your teacher could provide them. It really is, I guess, dependent on whatever happens in your class. Okay, but I'll show you on regular graph paper because that's what most people have. How do you draw this? Okay, so let's start with the axes, the black lines. This is like your regular 2D Cartesian plane, right? Okay, so instead of having your horizontal axis as your x, it's now going to be your y. Instead of your vertical axis being your y, that's now your z. Okay, so you would draw those two first so that it looks kind of like a cross. Now the x-axis, which is the third one, is a little bit trickier. You're just going to go from this part straight through the origin and into the next portion. Okay, so it kind of looks like part of it's coming out of your paper and the other part of it's going into your paper. All right, so again, I'm going to show you how to do this, so don't worry. Now, how do you put numbers and scale onto these axes? Well, it's kind of similar to the 2-dimensional plane where you have your positives along your horizontal axis there. And that doesn't really change. So on your y-axis, this is your positive branch, like 1, 2, 3. Your negatives would go over here normally, right? So that doesn't change either. This is your negative branch, negative 1, negative 2, negative 3. Positives would go here on your vertical. Positive 1, 2, 3. So I'm just following the boxes. Okay, negatives go down here. Negative 1, negative 2, negative 3, whatever, wherever the lines are. Okay, now the x, which is the new one, this is going to look like it comes out of the paper, and that is your positive branch. Okay, so positive 1, positive 2, and positive 3. The negative goes into the paper, negative 1, negative 2, negative 3. Okay, so now you can see all of your positive branches and all the negative branches of your axes. If you forget, there is something called a right-hand system, and it shows you where the x, y, and z positive axes are. Okay, so let me show you how to draw this, and I'm not very good at it. But, okay, take your right hand. First, figure out which one is your right hand. Okay, and take your right hand. You guys got it? All right. Now take your ring finger and your pinky. So your ring finger is your 4th finger, and your pinky, your smallest finger, and place them against. Is your pinky the smallest finger, or is that your thumb? Is your thumb a finger? Okay, now we're getting philosophical here. Take your 4th and 5th fingers and place them against your palm. All right, so it should look like, oh geez, I'm not a great drawer. There's your palm, your wrist, okay, and your 4th finger should be lying like this, and your pinky should be there. Okay, now stick your thumb out. This is going to be your thumb. All right, now at a right angle, I want you to stick your index finger out. And at another right angle, try to stick your middle finger out. Okay, so that is called the right hand rule. Basically, your 3 fingers are kind of like equal distance to each other, and you have this like alien claw that's like staring you in the face about to eat you. Okay, so this right-hand system just shows you where all of the positive axes are. Your middle finger is your x-axis, your z-axis is your index finger, and then the y-axis is your thumb. Okay, so if you ever needed to, I don't know, visualize three-dimensional vectors, you can always use your hand. Okay, so let's move on. Get rid of this diagram. Okay. In the past, you had called these your quadrants. Like this should look pretty familiar. Okay, and I want you to think about it for a second. Quadrants, quad, 4, right? Quad means 4. So there are 4 sections. Now, when you're talking about the 3-dimension on the left-hand side, the 3-dimensional coordinate system, you obviously have more than 4 sections. And so we actually have 8. And I'm going to try to number them off. I don't think that this is the right order, but I don't really think order matters. Okay, so this is your first quadrant, octant, second octant, third octant, fourth octant. So those are your 4 front octants, and there are 4 more at the back. So you got your 5, 6, I don't even know where to put 7, I guess, is the one at the very back, and 8. Okay, so there are 8 sections where your coordinates could be placed. So for example, if you're talking about, say, a coordinate over here, your x and y, because it's only 2 dimensions, right, would both be positives. But if I'm talking about, say, octant 2, in like any coordinate within this section would have an x, y, and z. Okay, it would encompass the positive x, a negative y, and a positive z. Okay, so for instance, I mean, you could have, say, 3, -1, and 5 would belong within this octant. Okay, so we've talked about the coordinate systems and compared them. Let's actually show you how to draw them. So this is a fun part. All right, so they're asking you to plot this point. And a +2, +1, +3, you can expect it to be in like the octant number 1 because it's all in the positives. Okay, but anyways, let's take a look at what it looks like. All right, the first thing you're going to do is you are going to draw the axes. Okay, so start off with your z-axis. Okay, so there's z. Then what you're going to do is you're going to draw your y-axis. So something like this. Similar to how you drew, your 2D ones before, but different letters. Because the x is going to go like this, so try to start off at the corner of a box. Go through all the corners like diagonals, through the origin, and then continue on somewhere there. Okay, you don't have to end off in a box like corner, but it just has to go diagonally through the origin. Okay, so something like that. You can put your scale. In fact, I'm pretty sure your teacher would expect you to put a scale. I'm not going to, mainly because it's hard to see in a video. Okay, so I'm just going to count it verbally. All right, so first we're going to start off with the x, +2. That's where 0 is, +1, +2. So 2 is right there. Okay, you don't have to put the dots. I'm just showing you my counting. Okay, the next one is the y, which is a +1. Okay, so positive on the y branch is right here. So that's going to be my +1. All right, so this is how you draw it. You kind of create a rectangular prism, which means like a box. Okay, and so the box, like the base of the box, is going to look like a parallelogram. I'm going to start off by drawing that parallelogram base. Okay, so this is what you do. Create the top and the bottom of that parallelogram. So notice that I had gone 1 unit because the y-axis is our horizontal. And so I went horizontally 1 unit, which means that that bottom, this guy, also has to be 1 unit. All right. Now I'm going to draw the sides of my box, which are like the sides of the parallelogram. So you're just going to connect it like this, and then it has to be the same on the other side as well. Do you guys see the parallelogram? That's going to be the bottom of my rectangular prism. Now what's going to give your rectangular prism some height is the up and down axis, which is your Z. So it's saying that you want to go up 3, and if we were to count, it's going to go 0, 1, 2, 3. So it should get up to this height. So this is my trick. Every corner of your parallelogram, you're going to go up 3 blocks. Okay, so 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Oh, and use a ruler. Okay, please use a ruler. Okay, so you're starting to see the height of my rectangular prism. Now what you're going to do is draw, like finish it off. You got to put a top on it, right? So just connect all of those sides. And there you go. That's the box. Now your teacher would expect you to have this all dotted. Okay, so this should be a dotted box because that's not actually what our final answer should look like. That's not what we're looking for. It's just to help us kind of gain like perspective in order to draw the final answer. Now the final answer is actually not coordinate P. What you want is a vector. Okay, so we want a vector of the position vector for P. Okay, so what I want is starting at the origin, going towards P. This is the position vector. That's what I'm going to draw in green. That's what the final answer should look like. Okay, so first of all, using the box, where is P? Okay, so P is, don't draw this, guys. Okay, just watch me. Starting at 0, I'm going to go 2 on my X. I'm going to go 1 to the right for my Y and go up 3 for my Z. This is where P is. Okay, so now that I have that in mind, I'm going to go from the origin, I'm going to point my arrow towards P, and that is my final answer. Okay, so the box should be dotted, the arrow should be solid. All right, I have 2 more examples at the bottom, and I'll show you exactly what should be shown. But I'm going to show you one more example, example number 2 together with the solid lines, again, because it's just easier to see in a video. Okay, so let's start with our Z, our Y, and X is going to go through the origin diagonally. Okay, so X, Y, Z. All right, start off with the 2 first numbers, your X and your Y. Okay, so the X is positive 1 starting from the origin. This is 1. Okay, so I'm just going to put the 1 right there. Negative 3 on the Y is going to go left, so negative 1, negative 2, negative 3. Guys, again, don't put the dots. I'm just using the dots to help me count to show you, okay, through the video. So that's a negative 3 right there. Okay, so with those 2 numbers, you're going to draw your parallelogram, which will be either the base or the top of your box. Okay, so here is the top of the parallelogram, nice and straight to the origin. So that's 3 blocks. Make sure that starting from the 1, you also go 3 blocks because this is going to be the side of your parallelogram. And that's why I went to the left, because I'm going to be creating that final side of my parallelogram. Okay, so with those 2 numbers, you're going to create a 2D parallelogram with just the X and Y plane. Okay, all right, now you're going to give it some height. So your height is going to be your Z. And it says negative 2, which means we want to go from the origin 1, sorry, that's 0, 1, negative 1, and negative 2. It should reach that point, so you're going down. That means that each of your corners of your parallelogram go down 2 blocks. Okay, so let's start off at the origin, 1, 2. Start off here, 1, 2. Okay, go in here, 1, 2. And then there, 1, 2. Okay. Now you're starting to see your box form, and we'll complete it by joining all 4 sides and getting that parallelogram at the bottom. So there's your box, and this should be completely dotted. Okay, so the final answer is not Q. You want the position vector for Q, which means that you start at the origin and you end at Q. But first, where is Q? Okay, so don't draw this, just imagine it. starting from the origin, go to +1, -3 on the y, and then down 2. This is where Q is. Okay, so that's where I'm going to aim for. I'm going to erase that because I don't want to draw it. The position vector is from the origin to Q. Okay, so the green is the only one that should be solid. Everything else should be dotted. And these are the two that I want you to try, but I've given you the answers for. Okay, so this is what it should look like, where you have everything dotted, but a solid answer at the very end. Okay, now that you know how to draw them, what I want you to do is figure out how to write them. Okay, so when I say them, I mean three-dimensional vectors. So when you have three-dimensional vectors, put into basis form, you actually have, remember the last video, we had an I unit vector, a j unit vector. Now we have an additional one called a k unit vector. So here's a review again. The I unit vector goes along the x-axis, and because it's a unit vector, I magnitude would equal to 1 unit long. Okay, so this is 1 unit long. All right, so if you think about it, this is at 1. So that coordinate right there that creates this position vector should have a 1 for the x, no dimension for the y, and no dimension for the z. Okay, so if I were to draw the unit vector for j, which would be created by a terminal point on the y-axis, you would have no dimension for x because it's lying along the y-axis. You'd have a 1 unit for the y-axis, and then it wouldn't go up or down, so 0. All right, and the k unit vector, which lies along the positive z-axis, 0, 0, 1. If you were to find the magnitude of any of these guys, so the length, it should equal to 1. All right, and I'm going to give you a formula to figure out the length or the magnitude of each of those vectors afterwards. Okay, but first I want to show you how to write them. So if you had a coordinate like this, 2, -2, 4, that would also represent a vector, right? The position vector for this coordinate. But how do you write that? Well, all this means is, and I wonder if I can do this in the colors, 2, that means 2 unit vectors along the x-axis, right? Because this is the x component, correct? Okay, then what you have is you're going to go, I like to use a lot of colors. There's my color, okay. Oh, I'm going to press it. All right, so the j would be, you're going to go -2, which means left 2, right? Because it's along the y-axis. This is the y. And I'm just going to put j as the unit vector along the y. Okay, and my last color is going to be this guy, which is my z component, a +4, and that's going to be +4 k unit vectors. Okay, so going 4 unit vectors upwards. All right, so that's how you write it in basis form, exactly the same as the 2D, except you have an extra component, which is your k unit vector. Now, if you wanted to go from this answer back into like a coordinate form, you know how before we had x and y coordinates and they were called ordered pairs? They're called ordered pairs because there's 2 numbers, right? But an ordered triple means that you now have 3 numbers. So all you have to do is you just check out the coefficients in front of each of the unit vectors, and that's going to give you your coordinates. So this is a +3. All right, so I'm just going to do this. This is going to be 1, -1, and +3. Make it simple. Okay, so if you write it in coordinate form or you write it in basis vector form, it really doesn't matter. They mean the same thing. It's just if all of a sudden on a test you're asked to put things into basis vector form, then you know what it is. Okay, so you guys know when we talk about vectors, we're talking about magnitude and direction. So those are the last 2 things that I'm pretty much going to talk about in this video. This is where it gets a little bit tricky because now you got to switch your brain onto 3D mode, okay? So try your best to follow. If you have questions, just comment below. So the magnitude of what we want is this vector, which is OP. Okay, it's the position vector for point P. Okay, and we're going to use a Pythagorean theorem. So first of all, if I wanted to know the magnitude, like the length of that vector, what I would need to do is I probably would need OQ first, which I don't really have, and then I would probably go upwards, right? So OP would be the resultant vector of OQ plus QP. So how do I get the red and the black vectors first? Okay, so the magnitude of OQ, which is the red one, would be, I mean, this is a right angle triangle, right? So couldn't I just use Pythagorean theorem, which is right here? This is already how you find the magnitude of a two-dimensional vector. All right, but now we're trying to find like a three-dimensional vector, and so that's why you got to do it again. You have to do, I mean, this is another right angle triangle, isn't it? Okay, so when I sub in OQ and QP into a Pythagorean theorem formula, I'm going to eventually get this guy. So notice that it looks exactly the same as my other cloud. This one is just one more component. It has a C at the end where there wasn't one before, right? So when you have 3 dimensions, you're going to have an A, B, and a C. And those A, B, and C just represent your X, Y, and Z. Okay? So basically you would be square rooting X squared plus Y squared plus Z squared to find the magnitude of a vector. This guy would just be taking your X and Y and going X squared plus Y squared and then square rooting it to find a two-dimensional magnitude. Okay, so I think you get that, but I'm going to add direction now. And I'm going to show you on this diagram before I actually move on to how you actually calculate it. Let's see if I can, this is really difficult to show you in a video, but I'm going to try my best. Okay, pretend that this is the vector that I'm looking for. There are 3 angles that it makes with each of the axes, your X, Y, and Z. Okay, so there is an angle that it makes, like it actually makes a right angle triangle with the X, and the angle is right here. Like you're gonna have to use your imagination, okay? So like it's in between your positive X axis and your position vector. This guy we're gonna call alpha, okay? Now there is another angle that we position with the position vector and the positive Y axis. That is called beta. The positive Z axis makes an angle, and all of these are right angles, okay? Like, sorry, not right angles, right triangles that it makes with the position vector in 3 dimensions. So the angle that positive Z makes with the position vector is called gamma. All right, and we can calculate each of those because these guys are going to be like how we find our direction for this position vector. So what I told you was just all of this. Okay, so how you find the angle relative to these axes. Now, how do you actually calculate it? You use any of these formulas. So remember how I said that they're created by 3-dimensional like right angle triangles? Like there's several right angle triangles going on all at once. Well, these are just cos is your adjacent over hypotenuse. Okay, cos is your adjacent over the hypotenuse. All right, so these are just like formulas in order to calculate your angles. So let's just say the very first one, cos alpha is A over OP. Let's see that in action. Example number 7 is right below. Find the direction cosines, or those direction angles, for this particular point right here. All right, so what you're going to do is you're going to take your x component, you put it at the top. Okay, if it's an x component, you're looking for alpha. All right, and then you put the magnitude at the bottom. So this is the magnitude right here, which we just found in the previous slide. Okay, so what you do is you take your 2, your -5, and your 3, you're going to put them all in the denominator, square them each, add them all together, and square root them. Okay, so this guy right here is your very first formula. Okay, so this guy right there. I'm sorry, I'm getting really messy, but I'm trying to just get you to follow what I'm doing. Okay, so the second formula, if you wanted to find cos b, or sorry, cos beta is this guy, and then cos gamma is right here. And you just solve like you normally would solve. Okay, so I got 71.02 degrees for alpha. Beta is going to be for 144.2 degrees, and gamma is 60.88. You can check it out and try it out on your calculator. Make sure that I did my math correct, because I don't always. All right, I'm a human being. But you guys can't be human beings, okay? You guys have to be perfect. I'm just kidding. Okay, the very last thing I want to go through is a unit vector. So we had already said a unit vector. Let's just say that this is a position vector, and we'll call it one letter, which is just u. If we were to find the unit vector for u, and we found the magnitude, it should equal to 1. Okay, so I've said that right over here. The thing is, though, you don't always get nice numbers, and so like when you have a vector, like a regular vector that has different numbers, how is it going to equal to a magnitude of 1 unit? Like, how do you find the length of it and it equals to 1 unit? Those are all weird numbers, right? So you have to force it. And the way that you do that is you take each of those components, the 5, the -2, the positive 3, and you take the magnitude of all of that. So remember, magnitude is like this formula right here. Okay, and you just put them into fractions and divide each one of those components by that magnitude. Okay, so you can kind of see it. Let me just move down. Okay, you can see it right here. So you take each of those components, divide it by the magnitude, and I mean, if you wanted to make it look pretty, you could just take the, like you can factor out the denominator. So I factored out a common denominator of 1 over root 38. And that just leaves each of the numerators. So it looks prettier. It's the same thing, because if you imagine expanding, you'll just get whatever you got above. Okay, so this would create the ability to have a unit vector that equals to 1, okay, as a magnitude. And if you don't believe me, we can do a check. Okay, so I took each of the components, your x, y, and z, of that position vector. I put them into the magnitude formula, squared them all, added them all, square rooted everything, and just follow my math, guys. Ta-da! It equals to 1. Crazy, right? Like magic. Math magic. Did I tell you guys I'm a mathematician? All right, okay, so that is 2.1. Next video is going to be on 2.2.